So today we are going to solve the basics problem of the Putnam competition, and we are going to start it soon. I'm soon going to share the screen actually. So I'm sharing this entire screen. Okay, here we go. Okay, so we are going to solve this basics problem. Let's see what this problem says. It says that there is a domain, let's n, and there is a constant r such that there exists a function g where every set is product one-to-one function such that there is condition for all n. So I have to find. So basically, this question says that we have to find the largest value of r such that this condition is satisfied in the given domain. We can approach this problem very easily. I can see this function says something, but we have to check what we are seeing is actually true or perceiving is actually true or not. So this function is this. Okay, that's my largest real number r. Yes. Then g of n can be two cases. It's increasing or decreasing. These are the two cases that would be there. Only these two cases. Either it would be increasing function or it would be decreasing function. And let's check whether it satisfies to be an increasing function or a decreasing function. And I can see one more thing that increasing function can be two types. It could be uh, n to the power s kind or a to the power n kind. These two are increasing functions. So we have to check for these two also that value satisfies or not. And then we have to check decreasing. So firstly, let's check increasing function and let's suppose function to be g of n to be n. And g of n would be n. Simply as I say, n plus 1 minus n is always greater than equal to n to the power r. You can see this. This goes off. So it can never be greater from this condition. It can r can have a value 0, but it would never be greater than this. So we have to suppose some kind of other function that's increasing. So let's go to the format of n to the power s. Let's take n square. Okay. So if we go by this rule n plus g of n to be n square, if I say g of n to be n squared, then supposing g of n would be n to the power 4. And if I go with this thing like n plus 1 whole squared minus n squared is always greater than equal to n to the power 4r. That's the only condition actually. If I go with it, it says 1 plus 2n approximately, and it n is to the 4r. So it's a straight line actually. So if we try to plot this, it would be 1 here and somewhat value here. So for this condition to be met, it should be greater than or equal to. It would never be equal to. So this function, this side of function, should always be. Suppose it's 1 plus 2n. So our value maximum can have it as a linear function. So we can have r to be in 1 by 4 from here. Then this would line would be like this, right? And n into n. Slope might vary and they might intersect at a point. They won't be greater than The means this line would be greater than this. 1 plus 2n would be greater than n in given domain, given n. So we have got R maximum for this. Let's check whether it would increase, R max would increase or decrease. So I can see that if we suppose it g to the power n to be n to the power s, then n to the power s, n to the power n to the power 1 plus s minus n to the power s, and would simply go to as n to the power s squared into r. This could be a general function. And I can see this thing from here, that if whatever I do with these, it would be n to the power s minus 1's coefficient. And for this to hold s square, so this value should always be less than s minus 1. Means if there are two quadratics, then if this side is quadratic, then it must be linear or less than quadratic. Then only this condition will hold true. Otherwise, this condition would go false. So for such condition, we have to check whether the maximum R, what can it? I don't think so. It would go beyond 1 by 4. I can have a reason for this. I can see this because as soon as these powers go beyond 3, so suppose it's 3, so the left hand term would be quadratic squared, and it would be 9 into R something. So R would be, if it want to be 1.99, we want it for this power to be 1.99, let's suppose. Because it could not be quadratic, because if it's quadratic, it would intersect, or it might intersect any at any point. So we are supposing this. So if I say that 9R equals to 0.1.99, and R is 199 upon 900, and it's still less than 1 by 4, 0.25. It's less than 1.25. Because if I say that 1.99 by 900 would be approximately be equal to what? 0.2 for 119 to 0.22, and still less. And this function, this value of R will keep on decreasing as we increase S. So S increases, R decreases, so we get R max at S equals to 2, and then R max comes out to be 1 by 4. We have checked it for this. Means this function is increasing. Let's check whether this function has something to do with a decreasing function or not. Let's suppose it to be 1 by n. Let's suppose g of n to be 1 by n. It's a decreasing function. Then g of n would be n, right? Straight away. Check for decreasing. I will write check for decreasing. I although know that since it is increasing and we have got a value, but still I want to check it for decreasing. So we have better confidence and better concept relativity. So if these two functions say that g of n is equals to 1 upon n and g of n is n, so we can say 1 upon n plus 1 minus 1 upon n must always be greater than equal to n to the power r. I can say this. But how well I can say this? If I say this to be n plus 1 upon into n and n plus n minus n plus 1, and this comes out something to be negative of n into n plus 1. So there is no value of r to hold this condition, no value of r to hold this condition. Even if I put anything, because this is a negative decreasing function and it's n to the power, it's simply, it can be o n square or anything. So this value is always greater. So we have concluded, although we knew it, but we have concluded that the decreasing function does not work for us. Decreasing function doesn't work. But what can we say accordingly? We cannot say anything new from here, because we know we have got a maximum value 1 by 4. But can it Can this function possibly be a to the power n? Yes, it can go like that. So let's check. Suppose f of n, g of n is a to the power n, to be precise. So what should I say about g to the n composite function? It would be a to the power n. So this, let's check. A to the power n plus 1 minus a to the power n is always greater than equal to a to the power r into a to the power n. Now we have this function in drastic way. What I can see is I can take a to the power n common and it would be left with a minus 1 and a or a to the power n. We can go by the way taking log on both sides. So it's n log a plus log of a minus 1 is greater than equal to r into a to the power n into log a. I am taking this log this side. So it's n plus log of a into a minus 1 with base r into a to the power. Can you observe something beautiful here? That's the case. Oh, select option. That's it. So this is very negligible value. So we can neglect this. So it would simply be, I know this condition, and that condition is it that this function a to the power n is always greater than n, and it's contrary. So g of n cannot be a to the power n. So what we get, r max to be equal to 1 by 4. That's it, guys. We have solved the problem B6 of the Putnam competition, and we have taken simply the condition that gn can be either increasing or decreasing. We have for n to the power s and a to the power n, because these two kinds of increasing function could be there, and we have to check also for decreasing. Firstly, we have checked for n to the power s, and we concluded that our max is at most 1 by 4, it cannot be more than that. Then we checked for decreasing function, the function does not hold true, and then we went on for checking a to the power n, and we came to know that it does not hold, so our max value comes out to be 1 to the power 1 upon 4. So it's 1/4. So maximum value this function can attain, this r can attain in the given condition, and the given domain is 1/4 only, 1 by 4. Remember, this problem does not say that n goes beyond 0 and starts with 1, capital N starts with 1. That's domain starts with 1 actually. So that's all for today. I hope that's a good time, and we have completed this B6 problem explaining in few 10 minutes approximately. So next time I will be coming up with another problem of this same competition, and we will be solving it together. Thank you. Have a nice day.